Hello everyone, welcome to Brain Blitz Audios. Today, in this episode of NEET Preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today we're dealing with the chapter Magnetism and Matter. This is the fifth chapter in the physics syllabus for grade 12 in CBSE. Let's begin, right? Here is our first question. Which one of the following statement is not correct about the magnetic field? A. Inside the magnet, the lines go from north to south of the magnet. B. Tangents to the magnetic lines give the direction of the magnetic field. C. The magnetic lines form a closed loop. D. Magnetic lines of force do not cut each other. Let's look at our options. Option D says magnetic lines of force do not cut each other. This statement is true, because if you try to keep two magnets close to each other, if they have the same poles, they try to repel. So therefore, this proves that magnetic lines of force do not cut each other, because if they do, then they'll have two tangents, which means that they'll have two directions for force, which is incorrect. So option D is incorrect because the statement here is true. Option C, the magnetic lines form a closed loop. Unlike electric field lines, magnetic field lines do form a closed loop. Passes from north to the south, and then inside the magnet it goes towards the north. So then the cycle repeats over and over again. So the magnetic lines form a closed loop. The statement is true, which makes option C incorrect. What about option B? Tangents to the magnetic lines give the direction of the magnetic field. Well, magnetic lines are curved, so therefore in order to give their direction, we need to find a tangent. So therefore option B, the statement is right, which makes the option incorrect. Therefore, the only option which is right, the right answer is inside the magnet, the lines go from north pole to south pole of the magnet. This statement is false. The correct statement is that outside the magnet, the lines go from north pole to south pole of the magnet. As you can see, from the north, the curved line begins and then it ends at the south. So it's moving outside the magnet. Whereas if you look at inside the magnet, then the magnetic field line moves from the south pole to the north pole in order to prove that statement C is true. So the magnetic field lines form a closed loop. So therefore, if the north to south direction is taken by the magnetic field line outside the magnet, then inside it has to be south to north. So therefore, option A, inside the magnet, the lines go from north to south of the magnet, is false. The statement is false. So therefore, the option becomes correct. Remember, the question is asking us the incorrect statement. Next question. Which one of the following are used to express intensity of magnetic field in a vacuum? Intensity of magnetic field in SI units is represented by ampere per meter. Now, when we look at our options, you find that option B, Tesla, is the SI unit, while option C, Gauss, is a CGS unit. But both of these become incorrect because they are the units for magnetic flux density. So therefore, options B and C are incorrect because these are the CSI or CGS unit for magnetic flux density. That's a different quantity. The right answer, the unit which is used to express the intensity of magnetic field, is option A, Ørsted. Ørsted is the CGS unit for this quantity, intensity of magnetic field in vacuum, whose SI unit is ampere per meter. And since option A is correct, that makes option D incorrect because Ørsted is a unit for intensity of magnetic field in vacuum. Next question. A frog can be levitated in a magnetic field produced by a current in a vertical solenoid placed below the frog. This is possible because the body of the frog behaves as. We need to find out which of these magnetic properties does the body of the frog behave, whether it's paramagnetic, diamagnetic, ferromagnetic, or antiferromagnetic. So the frog, let's draw a blob for that, is levitated in a magnetic field produced by a solenoid. And this happens due to repulsion. Therefore, since the body is levitated, we can say that there is the possibility that the frog can be strongly magnetized. So if the body of the frog is magnetized and then the poles are opposite, then repulsion occurs. A high amount of repulsion occurs, which can be strong enough for us to levitate the frog. Now, a material which can be strongly magnetized is option C, ferromagnetic. That's the reason why ferromagnetic materials are used to make magnets, because they stand permanently. So if a frog has a ferromagnetic body, then this frog can be strongly magnetized, and then therefore using repulsion, we can use the magnetic force in order to levitate a frog. So for that, the body has to be strongly magnetized, and that is possible only if the frog's body behaves as ferromagnetic. If the frog's body is paramagnetic, then you can only have weak magnetization. If the frog's body is diamagnetic, again, it's impossible because the diamagnetic substances, they do not let the magnetic field lines to pass through them, so no field. And antiferromagnetic substances are not used in making magnets. So strongly magnetizing property is for ferromagnetic substances. Next question. Liquid oxygen remains suspended between two pole forces of a magnet because it is diamagnetic, paramagnetic, ferromagnetic, or antiferromagnetic. Okay, so let's draw this diagram. Imagine we have two monopoles, a north pole and a south pole, and we have an atom, a molecule of liquid oxygen. So now there is a force which attracts the liquid oxygen molecule towards the north. At the same time, there is an equal and opposite force which attracts the liquid oxygen molecule to the south. Because the reason why we can write this is because in the question it says liquid oxygen remains suspended. So in this situation, we find that there is attraction towards both poles. Both the North Pole and the South Pole are attracting liquid oxygen. The force on the north will be equal to the force on the south. Now, north and south poles of a magnetic field can only attract an oxygen molecule if there is a weak magnetic force which is acting towards both poles. The reason why it is not strong because one material cannot be done into two at the same time. So therefore, if we look at our given options, diamagnetic, paramagnetic, ferromagnetic, and antiferromagnetic, we can find that option B is the right option, because in option B, a paramagnetic substance, the substance can be weakly magnetized if in, say, a magnetic field. So therefore, it can have attraction towards both sides. In option A, diamagnetic, there will be, once again, no field lines passing through the magnetic field. And so option A is incorrect. Option C, ferromagnetic, we will have strong attraction towards one pole. So that is incorrect. An antiferromagnetic, it's again strong, medium repulsion from one pole. So therefore, the right answer is option B, paramagnetic, because it's getting weakly attracted to both sides, and therefore that happens only in a paramagnetic substance where the dipole moments of the atoms get magnetized with the external magnetic field. Next question. The magnetic susceptibility of an ideal diamagnetic substance is -1, 0, +1, infinity. Now, what is an ideal diamagnetic substance? An ideal diamagnetic substance is a substance which removes all magnetic field lines induced by an external magnetic field inside it. And when we look at the quantity magnetic susceptibility, it is the degree of magnetization of a material in response to applied external field. When it comes to diamagnetic substances, the magnetic susceptibility measured by Xi is always between -1 and 0. For magnetic susceptibility to be 0, there will be no removal of magnetic field lines. There will be no repulsion. And since an ideal diamagnetic substance removes all field lines inside it, therefore, the option here will be -1. So the value for magnetic susceptibility is -1, which is option A. If you look at option B, this will be for, say, no magnetic substance. So it's a non-magnetic substance which will have magnetic susceptibility to be 0, because then there will be no reaction to the external magnetic field, say plastics. So option B is incorrect. Option C, +1. This would mean that the object would be ferromagnetic, because to have a magnetic susceptibility of 1 means that the object can be strongly magnetized, which is possible for ferromagnetic substances. And for Xi is equal to infinity, that will also be for ferromagnetic substances. So options B, C, and D are incorrect. The right answer is option A, -1. For diamagnetic substances, the magnetic susceptibility is always negative, lying between 0 and -1. And since we're talking about an ideal diamagnetic substance which removes all field lines inside it, the magnetic susceptibility has to have its most minimum value, which is -1. Next question. A magnet makes 40 oscillations per minute at a place having magnetic intensity of 0.1 into 10 raised to -5 Tesla. In another place, it takes 2.5 seconds to complete one oscillation. So we have two different values. The value of the Earth's horizontal field at that place is. So how do we solve this question? So in this question, what we do is we use the formula for time period of vibration of a magnet. And let's suppose that this magnet is placed in the Earth's magnetic field, because vibration occurs in a magnetic field. Let's suppose that it's in the Earth's magnetic field. The formula for time, t, it'll be equal to 2 pi times root of I divided by mh. Now over here, m is the magnetic moment, I is the moment of inertia of the magnet in vibration motion. Both of these are constant for a magnet. So if we are using the same magnet here in this scenario, we're using the same magnet for two different scenarios. So therefore, I and m will be constant. 2 pi is already a constant. So that leaves us with the relation time is proportional to the root of 1 by h. So time is inversely proportional to the square root of magnetic intensity. Now over here, let's consider the, let's say, time taken to complete one oscillation as capital T. So over here, 2.5 seconds will be T2 because it happens at the second location. And let's represent H1 as 0.1 into 10 raised to minus 5 Tesla, the magnetic intensity at the first place. And here we'll need to find out H2 and T1. Let's first find out T1. So in the first place, let's take time period of one oscillation as the total time taken divided by number of oscillations. So therefore, the value of T1 will be equal to the total time taken is 60 minutes for 40 revolutions. So 60 by 40, that is 6 by 4, which is 3 by 2, which is 1.5 seconds. So now we have T1, which is 1.5 seconds, T2, which is 2.5 seconds, and H1, which is 0.1 into 10 raised to minus 5. So again, the relation is T is inversely proportional to the square root of H. So therefore, T1 by T2 will be equal to H2 by H1, the whole root. Plug in the values, you will get 1.5 divided by 2.5 will be equal to, H2 is unknown, let's write it as such, and H1 is 0.1 into 10 raised to minus 5. 1.5 by 2.5 is just the same as 15 by 25. So 15 by 25, that can be written down as 3 by 5 because both are divisible by 5. So 3 by 5 is equal to, then inside the root, we'll have H2 divided by 0.1 can be written as 10 raised to minus 1. So 10 raised to minus 1 into 10 raised to minus 5 gives you 10 raised to minus 6. So H2 divided by 10 raised to minus 6 inside the root. So over here, let's square it on both sides. So therefore, we'll have 9 by 25. 3 square is 9. 5 square is 25. Will be equal to H2 divided by 10 raised to minus 6. So over here, we can write H2 as 9 by 25 times 10 raised to minus 6. So let's divide it. So let's divide it right here due to the space. So 9 divided by 25. So 25 doesn't go into 9, so we add a 0. Put in a 0 next to 9, so point comes there. 25 goes into 93 times, that's 75. 115 remainder, again put another 0, that's 150. 25 goes 6 times, so 150 minus 150 is 0. So the value for H2, which is the magnetic intensity of the Earth in this question, will be 0.36 into 10 raised to minus 6. The right answer is option D, 0.36 into 10 raised to minus 6 Tesla. Here we use the formula for time period of vibration of a magnet. And this happens when a magnet is in a magnetic field. And so therefore here we're using the Earth's magnetic field for the experiment for this problem. And again, we found out the relation T is inversely proportional to 1 by h, root of h. T is inversely proportional to the root of h. And using that, we use the relation T1 by T2 is root of h2 by h1. We found out T1 using the question figures given. And then simple calculations gave us the answer 0.36 into 10 raised to minus 6 Tesla. And that is option D, which is the right option. So that concludes this episode of NEET preparation. We have made a lot of videos on NEET preparation. Don't forget to click the link of the playlist in the description down below to view more videos. And if you want to support our channel and gain more of our content, then don't forget to subscribe to our channel, Brain Blitz Audios. So until the next episode, take care, stay safe, bye-bye for now.